Hello everyone, a short circuited coil is placed in a time varying magnetic field. The electric power dissipated due to the current induced in the coil. If the number of turns were to be quadruple and the wire radius is halved, the electric power dissipated would be. So if I talk about the electric power, we already know electric power is EMF induced square by radius. And if I talk about the EMF induced, we already know from the Faraday's law that the magnitude of the EMF induced is equals to rate of change of flux, and rate of change of flux will be equals to, since the area is constant, so it will be N into A into dB by dt, where dB by dt is the rate of change of magnetic field, right? So here the magnetic field is changing and these two are constant for case 1 and constant for case 2. So we have to find out the ratio, we have to check whether the power decreased, increased, or what happened to power. So if you see the dB by dt is the same for the two, so the EMF induced is proportional to N into A, where A is pi into R square, number of turns times of this. So we can write the EMF induced is proportional to this. Now if you see the power is equals to E square, see the number of turn is quadrupled and the wire radius made half. So if I write down the power here, so power, as we know, it is proportional to E square, that is this square. So I will write here the changed power by initial power is equals to the changed number of turn, change radius whole square, initial number of turn whole square, and n dash is 4 times of n, and the radius is half of the initial radius, so it will be this. So you can see already this is 1 only, so it will remain the same. So B will be the correct option. Simple. Thank you.
In this problem, we have given that in the figure P and Q are two coaxial conducting loops separated by some distance. When switch S is closed, a clockwise current IP as seen by E. Okay, so E is an observer. So E observes that there is a clockwise current when switch S is closed. So there is a clockwise current in the loop. Okay, so current, there is a clockwise current ip in the loop. Okay, and an induced current iq1 flows in q. Okay, so there is iq1 current flows in q. The switch remains closed for a long time. When switch S is open, the current iq2 flows in q. Then the direction of iq1 and iq2 as seen by er. Okay, so first of all, when clockwise current flow in ip as observed, as observed by an observer E, then there will be, due to the clockwise current, there will be the direction of magnetic field induced in the loop will be like this. Okay, so this will be the direction of magnetic field. This will be the direction of magnetic field. Okay, so this is the direction of magnetic field by the loop P on loop Q. So as the current starts to flow, suddenly the magnetic field will start to flow and it will increase. And if the magnetic field across the Q loop will increase, then flux across Q will also increase. And if there is a change in flux in Q, then there will be induced current I induced will also be developed in coil Q in such a way, according to Lenz's law, that it will oppose the change in flux. So as the flux is increasing, is from right to left direction, so the current will be induced in the loop in such a way that the flux will developed in the direction from left to right. So the direction of current in this case, according to according to observer, will be anti-clockwise. So first of all, the current in the loop Q will be anti-clockwise. So IQ1 will be anti-clockwise as observed by E. As observed by E. Okay, now there is the second case. In the second case, we have given that the current initially the current is set up in the coil P, and this current is IP. Okay, now switch is open. So as the switch is open, then the direction of magnetic field, which was earlier from right to left in the coil Q, due to the current in the coil P. So this as the current reaches to zero in the P after the switch is open, then magnetic field also starts to decrease, and if magnetic field decrease, then flux across Q will also decrease. And if flux will decrease, then the current will flow in such a way that it will try to oppose the change in flux. So the direction of induced current in this case will be clockwise. So the direction of current for the second case for coil Q will be clockwise, as observed by as observed by E. So that's the answer of this problem. So respectively anti-clockwise and clockwise, that is option D is the correct answer of this problem. Thank you.
Hello everyone, let us start with our question. In this question, what is given? A coil of wire having inductor and resistor has the conducting ring placed coaxially with it. Now the coil is connected to a battery at time t equals to 0, so that time dependent current I1 is start flowing through the coil. Now I2 is the current induced in the ring. So I2 is the current induced in the ring, and Bt is the magnetic field at the axis of the coil due to IT. Now what we need to find? We need to find what is the basically product of I2 I2 and B with respect to time, whether it would be increasing or it would be decreasing, or it does not vary with time, or it passes through a maxima. Okay, now we know that magnetic field due to current at the axis of the coil, magnetic field as a function of coil as a function of time would be equals to what? Mu naught n into I. Okay, I1 we can call, because this magnetic field is due to the current I1, so we call that B as a function of time would be equals to mu naught NIT. So basically we are knowing that this B, this I1 and this I2. So basically these are function of time, so we are just writing it like this. Okay, noting that we are already knowing that these are dependent on time. Okay, I1. Okay, now due to this magnetic field, okay, so there would be a EMF which would be generated by due to the change in the magnetic field. So E value would be equals to d phi over dt. If we take the modulus, so it would be d phi over dt. So we can say that it would be equals to phi would be phi would be B into A. So if A is constant, so it would be A times dB over dt. Okay, so we can write this value as, because mu naught and n would be constant. Okay, so we can write it as A mu naught n di1 over dt, because we know that I1 is dependent on temperature, sorry, this time. We have already stated that. Okay, now this is the value. So we can just treat this as our constant. We can say that E would be equals to some constant. Let's say this is the constant K1 and then di over dt. Now what is the value of current I2? Because current I2 is due to this induced EMF. So we say that I2 would be equals to E divided by R. Okay, so we can write here as K1 di1 over dt divided by R. So we can treat this as our another constant. We can say that it is just equals to K2 di over dt. Okay, now what would be the value of this I1? So basically it would be an LR circuit. So I1 could be written as, for an LR circuit, I1 would be equals to I naught, okay, 1 minus e to the power minus t over tau, where tau for an LR circuit is what? L divided by R. Okay, now this is the value of I1. So what would be the value of this B? So B would be equals to, because we know that B would be equals to mu naught Ni, B equals to mu naught N into I1. So we can write it as mu naught N I naught 1 minus exponential minus t over tau. Okay, we can write it like this. So we can take this result at some constant. We can just take this result at constant. So we can just write it as b equals to, we can, this is k2, we can say that it is equals to k3. Okay, 1 minus exponential minus t over tau, we can write it like this. Now what would be the value of the I2? So I2 would be just k2 times this differentiation of this value. Okay, so if we differentiate this and put into this equation, then our I2 would be, I2 would then turn out to be k times e to the power, we can just write the constant to be k4, e to the power minus t over tau. Why? Because if we see this, if we differentiate this expression, so there need not to be anything which could be differentiated. It would be equals to 0, and it would be e to the power minus t by tau. It is written like this, and then there would be minus 1 divided by tau, and which we have termed at to be constant, because ultimately we just need to have the variation of b with t, bt with time. So if we take the product of b and I2, if we take this product, multiply these two quantities, so b value we know that it is k3 times 1 minus e to the power minus t over tau. Okay, this is the value. And I2 is k4 times e to the power minus t over tau. So again, these values are constant. We can just term it as to be k5. Then it would be e t to the power minus t by tau 1 minus e minus t over tau. Okay, now this is the thing which we need to, this is the final function, our b into t2. Okay, this is the thing which we need to check. Now we basically we need to check. So if t equals to 0, if we put t equals to 0, so what would be this value? So it would be equals to 1, but it would be 1 minus 1. That means our this product bi2 would turn out to be 0. Now when t approaches to infinity, now what would be the value of bi2? Now if t would approach to infinity, then this term would be e to the power minus infinity, and e to the power minus infinity is 0. That means at t equals to 0 and t equals to infinity, our curve is touching the axis. Okay, because these values are 0, time axis it would be touching. Now that means there would be a maxima here. So to get the maxima, what we can do, we can just differentiate this our product bi2 with respect to time and put it equals to 0 for getting maxima or minima. For maxima, and in this case it would be maxima. So if we differentiate our this equation, so k5 won't be differentiated, so we can take k5 to be constant. Then we can differentiate our first part, so and taking it to be constant, so its value would be minus e to the power minus t over tau divided by tau, and then we need to take the bracket 1 minus e to the power minus t over tau. Okay, we have differentiated this our first part. Now we can take this part as to be constant, and we can differentiate this one. So from here the value would turn out to be, so this would be 0, and here it would be e to the power minus t over tau divided by tau. Okay, and this we can put it equals to 0. So this finally, if we calculate this, then our t value would turn out to be 0.693 times tau. Okay, that means, and if we calculate our d2 bi2 at this value, so this value would be less than 0. That means this is the maxima. Okay, so what would be our graph look like if we plot our graph? So it would be basically like this. So initially it would be rising, okay, and after some time it would reach its maxima, and at infinity it would turn itself to be a 0. So this is the product b into I2. Okay, and this is our time, and this is the time at which it reached the maxima. So which option would be the correct option for our case? And the correct option would be that it is not, every time it is not increasing with time, neither it is decreasing, does not vary with time. This is also wrong. So it passes through a maxima. So our correct option would be a D option. So hope you have understood this solution. Thank you.